portions to find equilibrium. I could do the simple math, right? Of course, just find the regular numbers, but I couldn't determine. I think that was a question during the video that you had asked. I couldn't determine well, at what temperature would equilibrium be reached, right? So
Okay.
maybe you probably going to touch on that again today, anyways. But I
Um,
think that was good again.
it's a great question. So the condition for equilibrium is always going to be energy in equals energy out. Okay. And so remember when we had multi levels of atmosphere, you set the equilibrium condition by calculating how much energy was coming in. We used the solar constant and the albedo to figure out how much energy was coming into the planet. And then for energy out, the top layer had to be sending that amount of energy, the same amount of energy out into space, right? Because then energy into the planet equals energy out. Okay, that's our condition for energy balance. And then in a lot of the climate examples, like you did for Krypton, once you know the energy going out of the top layer, then that helps you figure out how much is going into the top layer, which then tells you how much is going into the layer, coming out of the layer before it. And you back calculate all the way down till you figure out how much energy is coming down from the atmosphere onto the planet, right? And then when you have those two numbers, how much is coming from the sun into the planet, and then how much energy is coming down to the planet that's being reflected down from, the lowest level of atmosphere, those are your two energy ins to the planet, right? And so we know that the planet is then going to have to send the same amount of energy out up
Yeah,
to the layers. And so now you've figured out how much energy the planet is radiating, right? And so it's radiating as a black body. So then you can use the Stefan Boltzmann relationship, which tells us, here's the how much energy is being radiated to what the temperature of that object must be. Okay. Now the way Stefan Boltzmann is written, let me just um, pull out these older ones just real quick. Let me share the screen. I'm sure a lot of folks will be happy you asked this question because it helps us kind of figure stuff out. So I'm going back to an old climate one, where we're putting on this energy in equals out constraint. Um, and this is our Stefan Boltzmann equation rewritten so it's solved for temperature. Let me show you the original equation. Let's see if I got it here. Yeah, here's our power per unit area equals the Stefan Boltzmann constant times temperature to the fourth, right? And so if you know the power, Stefan's Boltzmann constant is 5.67 times 10 to the minus 8. Then if you know the power per unit area and the Stefan Boltzmann constant, you could figure out the temperature. Now, often this is used, you put in the temperature and it tells you how much power is coming out. But in the case of, what you did in Planet Krypton, or in the case of this energy balance stuff, we're figuring out how much power is being radiated out of the planet, which is this term. So then we have to solve for temperature, which means you're going to have to divide by the Stefan Boltzmann constant on both sides, and then take the fourth root of that number, right? And so in that case, that's where this is coming from. So you would put in the amount of energy that's radiating out of the planet, divide it by the Stefan Boltzmann constant, take the fourth root of that, and that gives you the temperature that the planet has to be to put out that much energy. And that much energy is, once it's filtered through all the levels of the atmosphere, will lead to an energy out that leads to the same amount as energy in. And then that's when the planet stops cooling or warming, and that's its new equilibrium temperature. You look a little bit confused? Let me go to climate model here with a 1-layer atmosphere. We knew 238 was coming in. So in order to satisfy the criterion that energy in equals energy out, we're talking about energy out back into space, right? And so if 238 is coming into the planet, 238 has to be going out into space. Where does that come from? The most outer layer of the atmosphere. And so if 238 is going out, that means 238 is also going in the opposite direction, which means that the amount going into this atmosphere has to be double this number, right? So that means the amount of energy going into this atmosphere here has to be this plus this, which is 476. Now we know how much energy is radiating out of the planet. And the way it radiates out of the planet is through black body radiation. So now we just need to figure out what temperature of a black body would emit this kind of energy, okay? And because we're doing it in watts per meter square, we don't have to worry about how big the planet is or any of those kinds of things. So we just take this number, plug it into this equation. So we're going to divide it by the Stefan-Boltzmann constant. And remember, Stefan-Boltzmann is 5.67 times 10 to the negative eighth. So when you divide this number by something that's 10 to the negative 8, it's going to give you a really big number, but you're going to take the quarter root of that, right? The square root of the square root, and that's going to give you a reasonable number. And in this case, to generate 476 watts per meter squared out of the planet into the atmosphere, the planet would have to be 303K. And so that tells us what that planet's temperature is. And that's the temperature at which now we've satisfied the energy leaving the planet is the same as the energy coming in. Because if the amount of energy coming in is greater than the amount leaving, then we're accumulating energy, which means that our temperature is going to have to rise. If the amount of energy coming in is less than what's leaving, then we're going to cool off until the amount of energy we're sending out is equal to the amount we're taking in. We always go towards that equilibrium position where one is equal to the other. Is that helpful at all?
Yes.
Okay. So what we talked about last time, and in the video you watched, we use this example where we say, okay, let's start with an Earth with no atmosphere, and we can figure out what temperature it should be, right? If 238 is coming in, then 238 must be radiating out. And for a black body to radiate out 238 watts per square meter, we can figure out what temperature that has to be through the same thing. We divide this power divided by the Stefan-Boltzmann constant. We get a big number. We take the fourth root of it, and this gives us the temperature. And it's really easy to do the fourth root. I think I had a little thing in that video on how you can use Google's calculator to take the fourth root. If anybody needs more clarification on that, I'm happy to do that. Google's calculators are pretty decent. And so with this example, okay, so we've calculated what the temperature has to be. And now our topic is transient warming, okay? So we've talked about the equilibrium condition. And so now we're going to discuss what happens before you reach equilibrium, okay? And so what we said is, imagine you instantly add an atmosphere to the planet. What are the fluxes going to be the instant after you add the atmosphere, okay? And so we know that 238 is coming in, and the instant you've added the atmosphere, there hasn't been time for anything to heat up or react, right? And so the temperature of the planet is still that 255K that we calculated, okay? And so that means we're still shooting out 238 into this atmosphere. But if we're only putting in 238 in the atmosphere, remember that energy is going to be re-radiated half upwards and half downwards. So only 119 is going out into space in the instant after that layer was added. Okay. So what does that mean? That means the energy coming in, 238, is much greater than the energy leaving the planet, which is only 119. And so if we do the calculation of energy in minus energy out, we've got 238 minus 119. And so that means the planet is accumulating energy at this rate, right? It's accumulating energy at 119 watts per meter squared, because that's how much more energy is coming into the planet than is leaving the planet. Are we all good on that so far? Talked about this last time. We're the instant after we've added the layer, time, there hasn't been sufficient time for things to reach equilibrium, right? We know that the planet will warm up because it's accumulating energy, and it will keep warming until the amount of energy being sent out is equal to the amount of energy being sent in. So since we know that it's accumulating energy, we can say, okay, it's going to warm up. And so we could say, well, let's pick, let's take a look and pick, a second, just looking at this. So we know the surface is accumulating energy at this amount. So we know it's going to heat up. So let's look at a higher temperature. It's at 255 now. We'll look at what happens when it gets up to 270. We're still taking 238 in. A black body at 270 radiates at 300, and we can use the Stefan Boltzmann to figure that out. Okay. If 300 was going in the atmosphere, how much would be going out into space? I'm asking.
150.
150. Half will go out into space and half will come back. So now, have we reached energy balance yet?
No.
No, we're taking in more energy than we're taking out. And so we can do that calculation, energy in minus energy out. And that tells us that we're still at an energy imbalance. We're still accumulating energy. It's positive at about 88 watts per meter. Okay, so if we're accumulating energy, that means that we're still warming up. Although you'll notice that that number's smaller than the number we had before. Okay, and so we can say, well, let's go ahead and take a look at a higher temperature. If we know it's going to warm up, we could look at 295, calculate our fluxes. That's 429 for a 295 K body. And half of that will go out into space. Again, have we reached equilibrium? No, we've got more energy coming in than we do going out. In this case, a difference of 24. Energy in, which is 238, minus energy out, which is 214. It's just going to give us plus 24. And so you can see it's still warming, but it's slower, right? And you can imagine where this is going. If we put all these things together, at 255, we had an energy imbalance of plus 119. Then when it warmed up to 270, we had less of an energy imbalance. And then when it warmed up to 295, it has less of an energy balance. And finally, it'll keep warming and accumulating energy until the amount of energy coming into the planet, 238, equals the amount of energy going out. What amount of energy is going out? That's half of what's going in this atmosphere layer. So if that's 238, this has to be 476. And then you can tell what temperature does the planet have to be putting out at 476. And that's 303 degrees Kelvin. And that's when energy in equals energy out. And that's the whole point of this idea of transient warming, is the minute you change something, it will take some time for the temperature of the planet to adjust until that energy imbalance is wiped out. And this is a key point here. If you perturb the energy balance for the planet, the temperature of the planet's going to adjust until the energy imbalance is wiped out. Does that make intuitive sense to everybody? Anybody
Yes,
have any?
Prof.
Okay. This takes time though, right? And to give you an idea of how much time it takes, let's look at an actual climate model where somebody's taken some computers and tried to figure this stuff out. And so we have some numbers that have been plugged in. And so here we've got a planet being simulated that's initially in equilibrium. And so this first plot, this is showing the global surface temperature in Kelvin over time, and you can see it's remaining constant. There's some fluctuation, but it's remaining constant. The temperature is not changing. Same thing with energy in equals energy out. It's initially in equilibrium, so that's true. And so our temperature isn't changing. Now, we suddenly add this lots of CO2 to the atmosphere. That's like creating a layer to the planet. And so now, if you look at the energy in or versus energy out, subtract the two, you can see there's a big energy imbalance to the tune of about 7 watts per meter. And it's a sudden shift. Okay. So now, what happens to the temperature? And this is what the model shows. We've had constant temperature. Then at the same time, when you have this flux here, year 2000, all of a sudden, this is now when energy in is more than energy out. You see the temperature shoots up very rapidly. Okay. It shoots up very rapidly. And this is when the mixed layer is warming up. So think of the mixed layer of the ocean. Remember, that's the first kilometer of the ocean where light and heat is warming up that water. It's being mixed by winds. So we call that the mixed layer, and winds and currents and various weather events. So that mixed layer, the exchange is pretty fast. And then you notice the change in temperature starts to slow down a little bit, right? This temperature change happened over just a few years. Whereas this peak, this starts to go much slowly, starts to warm up, and looks like it's taking hundreds of years, maybe even thousands. Anybody know what's happening here? If this is the mixed layer of the ocean warming up, what's this?
That would be the top layer.
So the mixed layer is the top layer of the ocean. And so once you've warmed up the mixed layer, remember the mixed layer is an exchange with the deep ocean. And so there's a lot of water in the deep ocean. Remember, 97% of the ocean is the deep ocean. The mixed layer is only like 3%. So that first 3% of water on the top warmed up really quickly because it's right on the top where all the energy is coming from. Remember, the infrared coming down from the CO2 atmosphere. And so that warms up fast, and then it has a slow exchange with the deep ocean. And so now it will take a long time for the temperature to finally get up. Because remember, we were talking about if you started at equilibrium and then you do a sudden change, we know it's going to have to start warming up if there's more energy in versus energy out. In actual climate, an actual planet, you know, how long does that take, and why does it take that long? Well, we've got warming of the mixed layer, and then the next thing we can warm up is the deep ocean. And so that takes thousands of years to reach equilibrium. So there can be some fast heating, warming up, and then some slow heating, but eventually, when it stops heating up, that tells us now that our energy in is equal to our energy out, and we don't have to continue to accumulate energy and heat up. Okay. Okay, so that was the end of last week's final lecture on transient warming. We're going to pick up on that in our today's lecture, which is called radiative forcing, which is the same idea. So we're not really introducing anything new here, but we're trying to really understand a specific point, which is that climate change in our context is going to begin with an energy imbalance being imposed on the climate. Okay. And in response, the temperature of the planet is going to adjust until the climate system is again in energy balance, right? So the climate we see today is a response to energy in versus energy out, and trying to put that energy flux into balance. And so let's go ahead and start with an example. Let's start with a planet that's got a solar constant similar to ours, around 3,000, a slightly smaller albedo, 0.6. We can figure out how much energy is coming into that planet. Okay. And if that's how much energy is coming into the planet from the sun, that means the amount of energy coming out of the planet's surface should be the same, which would mean the amount of energy coming out is 300 watts per meter square. And to figure out what temperature emits at that, we use the Stefan-Boltzmann relationship, solve for T, and we find out the temperature is 270 K. Okay. Hopefully that makes sense how we're doing this. We're using our favorite little equation here, and then we're just plugging in these values. Okay. And that gives us the 300 watts per meter squared. Okay. Now, so we can draw a flux diagram for that. We got 300 coming in, we got 300 going out. That keeps us at a 270 K. Sorry, I have the wrong number there. Imagine that the sun, for some reason, gets brighter by 5%. All of a sudden, the sun gets brighter. There's a big sunspot, something's going on, and the sun gets brighter by 5%. So that means we know there's going to be a change in energy, right? Before we calculated that the amount of energy coming in was 300 watts per meter based on the albedo and the solar constant. But now our solar constant has changed. It's increased by 5%. So I'm going to multiply it by 1.05. And so our new amount of energy coming in is 3150. Okay. Okay. And I'm sorry. Yeah. And so when we figure this out, that means our new, given the albedo of 0.6, that means the new energy coming in is 315 watts per meter square. Okay. So the energy is increased to 315. And again, the instant after the sun gets brighter, remember, temperature can't change instantly. There's kind of a temperature inertia. It takes a little while for things to warm up. So at the instant after the sun gets brighter, the energy out is still 300. That's what we calculated before. So now our energy in is more than our energy out. And so our temperature, we would imagine, is going to increase. And so if we plot this out, here's, this is year 0. this is where our abrupt, this is showing energy in right over here. So we get this abrupt change of energy in. And now if we were to look at the surface temperature, okay, it was at 270 and now it's going to start increasing, okay? And according to our models, it's going to increase quickly because we're going to warm the mix layer first. And then once the mix layer is all warmed up, it's going to start exchanging with the deep ocean and beginning to heat up the deep ocean, okay? So after this initial rise, the rise in temperature is going to be more slow, okay? Now, if we were to look at energy out, we saw that the energy out before was at 300. That was before the sun got brighter, okay? As it starts to accumulate energy, the energy out is also going to start increasing, right? But remember, the energy out is determined by the temperature of the planet, right? It's determined by the surface temperature. And so as you would expect, the energy out is going to increase just like the surface temperature is increasing, because it's the surface temperature that determines how much energy you put out, because it's a black body. So here's energy in minus energy out. And so what we see is at time 0, the two were balanced. The energy in minus energy out was 0, right? Because, 5 minus 5 is 0. So since they were equal, it was balanced. And then there was this sudden change where energy in was much greater than energy out. And slowly, as the energy out increased, this imbalance started to decrease, right? It came down quickly at first as we warmed up the mix layer and we could emit more energy from the mix layer, but then it was taking longer for the deep ocean to heat up over here. And so then the energy out, it took it longer for the energy out to increase. But once you increase the energy out, or energy in minus energy out, eventually that difference is going to fall back to 0. And that looks like it took about 2,000 years. Okay. In 2,000 years, the planet stabilizes. Instead of at 270K, it's reached 273. Might not seem like a lot, but remember, it's average temperature. It can vary a lot. Okay. So we're talking directly about global warming. Here's where our sun got brighter, right? And as it warmed, the energy imbalance was wiped out. And then the planet stabilizes at this new temperature. Okay. And so again, we're the same conclusion. I'm just using this as a second example. Before we quickly added a layer of atmosphere, now we've made the sun brighter really fast. The temperature of the planet's going to adjust in order to maintain that energy balance. And so if anybody asks you why is the Earth's climate the way it is, because that's the climate that balances energy in and energy out. And if we're changing, it's because we're trying to meet that new balance. And as you can see from some of these, that it takes a while. There's an initial quick change as you warm up the mix layer, but then a more gradual change, but still a change that takes place over thousands of years as you do the deep ocean. Okay. And so now this allows us to introduce this concept called radiative forcing. Okay. And radiative forcing is the magnitude of an energy imbalance that's imposed on a planet before the temperature adjusts. Okay. Its units are going to be in watts per meter squared. And we know that in response to this energy imbalance, the temperature of the planet will adjust to wipe out the energy imbalance. But radiative forcing is that difference in number that tells us, how much is it responding to. Eventually, equilibrium will be established at a different temperature, but the radiative force, that's the difference, the magnitude of the imbalance that has to be wiped out before the temperature can finalize. Now, notice there's no time component to this. We're not including any information on how long it takes for the adjustment to take, okay? In some of our models, we can, factor in the mixed layer and the deep ocean, etc. But for radiative forcing, it's just an amount of energy. That's the imbalance, okay? In our case of the sun increasing in energy, our energy imbalance when the sun first started shining brighter was about 15 watts per meter squared. Okay. And so that was our radiative forcing. That was the amount of imbalance that we then have to respond to change the temperature. And this is really, really important because radiative forcing is used to quantify these energy imbalances. And I'll show you why this is really helpful now that this is where all this has been leading to. You first figured out how to calculate equilibrium differences and what the new final temperature will be once it reaches equilibrium. Energy in when energy in will equal energy out. Then we looked with transient temperature, how that takes some time to do. And it's all about that energy imbalance and wiping out that energy imbalance. And that's our little quantity that we call our radiative force. Okay. And so here's an example of how it can be used. So let's look at carbon dioxide. We've recognized this as an important component of climate change, of man-made climate change. So we're going to look at the radiative forcing of carbon dioxide. And so here's a graph of how carbon dioxide has changed. And since radiative forcing values are changes, they're about changes, we use a reference period when calculating them, okay? And so these values are going to be based on the IPCC of 2019 and uses reference period around 1750, a little bit before, okay? And so what they've determined in all their papers, et cetera, is that the amount of change that we've seen in CO2 has been about 130 parts per million. So the amount of CO2 that's increased in our atmosphere has been about 130 parts per million. Okay. And they calculate from that a radiative forcing of about 2.15 watts per meter squared. So now we can correlate an amount of CO2 increase with an amount of what that energy imbalance is that the planet's going to need to adjust to. Okay. And the reason why it's so helpful is because now you can compare a lot of different things and their effects on future climate by looking at the radiative forcing that they're going to cause, the amount of energy imbalance that they're imposing on the system that the planet's going to have to adjust to before it can get back to the equilibrium condition of energy in equals energy out. So methane, for example, that's another greenhouse gas that we've identified. It absorbs in the infrared range. And so it's going to re-radiate down to the surface, increasing our temperature. If you look from from 715 to 9, it's been about a 1 part per million increase in methane. And IPCC calculates that it gives you a radiative forcing of about 0.54 watts per meter squared. So now you've got a way to compare what CO2 is doing to what methane is doing with quantifying numbers. Okay. So it allows us to compare these two. Okay. And that can be really helpful because now we can put all of the greenhouse gases to see, well, what's their radiative forcing? What amount are they contributing to this energy imbalance that the planet's going to have to adjust to? And so for carbon dioxide, we see that, it's a little over 2 here. For methane, we see, it's a little around 0.54 or 0.5 over here. Here's our radiative forcing. For halocarbons, it's probably around 0.3 watts per meter squared. For nitrous oxide, another important component of greenhouse gases that you see, that too, it is a positive radiative forcing at about 0.15. And same thing with low atmospheric ozone that also absorbs in the infrared and will re-radiate down. And so that will give us some radiative forcing. And so if you total all these up, the total radiative forcing from greenhouse gases is about plus 3.5 watts per meter squared. More than what we saw for carbon dioxide alone or for methane alone. So it gives us a good kind of idea of this is what our planet has to adjust to. Does it adjust to it instantly? No, we know it doesn't. We know the temperature will quickly rise while the mixed layer is warmed up, and then it still takes a lot longer to finally heat up the deep ocean so everything's at a constant temperature and we establish a new equilibrium. But this is an important number. The total radiative forcing from GHGs, that's a really important number because that tells us, how much more energy is coming in than energy is leaving out. Now, aerosols are also important when it comes to looking at climate change. So the dominant impact of aerosols is to really kind of increase the albedo of the planet. So these aerosols often will, in clouds, what clouds are is the water vapor. And they're condensing around little particles in the air. When you have more aerosols in the air, you get more of condensation around those aerosol particles. And so it leads to a whitening of the clouds, okay, makes them more reflective. And if we're reflecting more light back into space before it ever gets to the planet, then it's like increasing the albedo, okay? And we've been sticking a lot of aerosols in the planet. I've got a little video here to show you what kind of aerosol stuff we're doing. Pull this over. Let's see. Okay, here we go.
This animation shows the distribution of aerosols over the Earth. Blue shows sea salt aerosols, which are formed when strong winds lift droplets of water into the air and the water evaporates, leaving a salt particle. Red shows dust aerosols, which are lifted from the ground primarily in the big deserts of the world, like the Sahara. This dust can be transported long distances. Green shows carbon aerosols, which are primarily formed when biomass is burned. You can see these aerosols being emitted from regions where biomass burning is prevalent, such as over Africa and South America. White aerosols are sulfate aerosols, which form when fossil fuels containing sulfur impurities are burned. When this happens, the sulfur is released to the atmosphere with the other products of combustion. Once in the atmosphere, the sulfur gases react with atmospheric water vapor to form highly reactive small liquid droplets known as sulfate aerosols. Most of the sulfate aerosols are located in regions with a lot of manufacturing and lax air quality standards, places like China and India. While aerosols vary...
Okay, so that gives you an idea of where the aerosols are in terms of their impacts So here's our greenhouse gases. If we're increasing the albedo, that means we're reflecting more energy out into space. That means less energy is coming in. So our radiative forcing is going to be negative, right? It's going against the energy balance. There's less energy coming in than there was before. And so that's going to be a negative effect. And so if you look at just this direct effect from aerosols, I'll talk about indirect effects later. We're talking about negative 0.3 watts per meter. And if you combine all of these, and I'll talk tomorrow or Wednesday more about the indirect effect. But if you total all these up, we can see our total radiative forcing is going to be somewhere around 2.5 watts per meter square of what we've currently put into our atmosphere up until now. This isn't talking about what we're putting in later, but what we've put in now since 1750, this would be the radiative force from 1750. And what we'll find, if you do the calculations, that the global temperature rise that we've seen is a part of what would be predicted from that radiative forcing value. But remember, we get quick warming as we do the mixing of the oceans, and we still have a couple thousand years as we're warming up the oceans for that temperature to finally adjust. So it'll now allow us to kind of make some predictions about the future and how long, what kind of warming are we going to see initially, and then how much longer is it going to take to see additional warming. So I want to hear some.
Hello, Prof.
Yeah. Go ahead.
Hello,
Shepard.
Prof. Yeah, I wanted to ask on the issue of how humans contribute to aerosols. What about cloud seeding? Could it be another way?
So anything that increases our albedo, anything that increases the reflectivity of clouds, for example, like seeding clouds, certainly can decrease the amount of energy in and help us with that energy imbalance that we're getting. So that can offset maybe some of the CO2. So that could help with fighting climate change. And see, that's the nice thing, is now the way you're thinking about these things is in a very physics sort of way, what things really will affect this energy imbalance and lead to ameliorating problems with climate change. Now, this aerosol thing is kind of a big deal. It's helping us right now, but a lot of these aerosols are air pollution, right? Things that have really bad health effects for people that live in cities. A lot of people die every year because of bad air and air pollution. If you go into China, for example, their air is terrible. They have tons of pollution. They got lots of coal plants burning fossil fuels and just pouring them into the air. Lots of sulfur going into the air, making those sulfate aerosols. And so people are getting sick. Anybody who's got asthma or anything like that, can have serious health problems. And so around the world, including here in the US and Europe and even parts of Africa, they're taking steps to make the air quality better, have more pollution controls, put little things on cars so the pollution out of cars isn't so bad. It used to be a lot worse in places in the US than it is now. But as we clean up the pollution in our air, we're now going to magnify our problems with climate change because we're no longer going to have this increased albedo. It's going to go in the other direction, and we're going to start getting more energy in and have to deal with more of this radiated forcing. But I like your idea of cloud seeding. Big difference, right? Now, pulling CO2 out of the air, we know is really, really important. And we talked last time and the time before that of how, you know, the global carbon cycle, when you have more CO2 in the air, how plants actually increase their rate of photosynthesis, you know, and that helps us. Well, there are folks in, I think it's in Washington State. There's a company there where they're using biotechnology to genetically engineer plants so their photosynthesis occurs at a double rate. So the plants grow twice as fast. So they're much more efficient at pulling CO2 out of the atmosphere. Now, isn't that a cool way to use biotechnology to actually not just mitigate the effects of climate change, but directly try and combat climate change by pulling CO2 out of the air faster by designing these plants? Because people have calculated how many new plants you would have, how many more trees you would have to plant to get rid of all the CO2 that we've just put in our atmosphere. And the number is too large to do. But by making plants more efficient genetically at fixing carbon, you know, that would be a fun project to work on that I'd love to be a part of, because it's using biotech really to save the world. And I think when in one of the courses you're going to have to take in the series in the program is going to be plant biotechnology, and that's going to be one of the examples that you get to talk about in that class, see the genetics behind it and how to do that. So that should be hopefully terribly interesting. So hopefully you'll enjoy that. Does that answer your question?
Yes, Prof. I know cloud seeding from agriculture for the rains, yeah.
Mm-hmm. Are there other questions anybody has? Okay, well, it looks like I've gotten nearly all of the pure teachings in. I think there's one I'm still waiting on. I like to wait till everybody has theirs in before I start grading them, because once I start posting, you know, people's up there, that becomes visible to all, then I don't really continue to collect them. Glory, I still think I need yours on Planet Krypton, basic climate modeling. So when you can do that, let's see, Nanamungo, I've got yours, Shepard, I've got yours, Caldrian, I have yours, I have Brenda's, but that's it right now. So if you can get to that next day, that would be great, because I'd love to start posting my responses. And this Friday, we're going to have a guest lecture from Dr. Farusa. Hopefully it'll match, you know, where we're going to get into this now. We're going to talk about specific things that affect climate change. And now we have a number that means something that we can ascribe to them, which is this radiative forcing number. And when you look at things like the IPCC, a lot of what they discuss in what's causing climate change and how much climate change is it causing is in terms of radiative forcing. That's how climate science deals with that. And so now you guys will be experts on this, which is great. Okay, everybody, thanks for your time. I will post this in an hour or so. And again, you know, rewatch some of the lectures. Shoot me questions. I'm always happy to answer them. Thanks a lot. Bye-bye.
Bye-bye.